Welcome to the second part of lecture 4. It's pre-recording scheduled for the second half of the first lecture in the second week of this 8-week summer course on algorithms. So in this part we focus on the depth first search algorithm and on some applications of graph traversals. To make it self-contained, in this lecture I will briefly go over the notations. A graph is given to us by two sets. The first set stores the vertices, so n is the number of vertices. The second set stores all the edges, all the connections between the vertices, and the important number there is m. It's important to realize that m can be as low as n, even one less in case the graph is a tree, or it could be of order n square. So we will formulate the cost of our algorithms in terms of n, in terms of m. And we will show that in the second half that the depth first search algorithm has exactly the same upper bound n plus m as the breadth first search. So they are both efficient algorithms, even though they are rather different from each other. When we speak of implementing, we talk about choosing the data structures. The data structure that we will use for representing graphs and trees is an array of adjacency lists. Why is that? Because in many examples, the number of edges is indeed of the order of the number of vertices. And this representation allows for a quick computation of the degree of each vertex. So the number of nodes that are connected to any given node. That is the degree of a node. So this is the representation that we will be using. So I will scroll now through to the main result of the first part. So this is an important theorem that we have proven. The breadth first search algorithm runs in time n plus m, the sum of the vertices plus the edges. So this could still be a quadratic running time in the number of nodes in a completely connected graph. But typically it might be linear in the number of nodes, which is an efficient algorithm and in some sense a very efficient algorithm, if you like. All right, that was the brief recap of the first half of the lecture. Now we are focusing on the depth first search algorithm, which is kind of a prototype for finding the exit in a maze. So when to choose the breadth first search or the depth first search, well, the trees are typically completely different that are computed by these two algorithms. And in some cases they are the same, and that was one of the exercises of the previous lecture, or we terminated with that. With the breadth first search, we get the shortest paths. With the depth first search, we actually might get the quickest answer to the question, the original question, given two vertices, is there a path between those two vertices in the graph? So the exit in a maze is kind of the prototype problem, or a little bit more urgency, escaping a burning building. So in the breadth first search, we are layering the vertices. layer after layer, and we have proven that in each layer we contain the vertices that are in the shortest paths to the root. Here, actually, if we want to exit a burning building, we want to exit. We don't really care that much about finding the shortest path, or that is really also, if we would know this, that would indeed very good. But as soon as we have one neighbor, we don't explore the siblings at the same layer, at the same distance from the root node, but we immediately go to the next first neighbor of the current node that we have. And then we backtrack if we hit a dead end. So um, that is kind of the grand overview. In terms of algorithms, we will prove in the second half that depth first search has the same worst case upper bound. So in some sense, in terms of efficiency, worst case running time of algorithms, it doesn't really matter which algorithm that you use. In theory, in practice, if you think about escaping a burning building, in the worst case, you're dead. And in that case, it might really matter that you use the depth first search algorithm. So the textbook also introduces depth first search as another way to get to more efficient search patterns. Okay, typically in the previous lecture, we used a recursive natural formulation for the depth first search. Here we will use a stack. So by a stack, that's another important data structure, we can translate every recursively formulated algorithm in an iterative one. And that is needed here when we talk about implementing an algorithm. We talk about choosing and making very explicit the data structure that we will be using. So when we do the depth first search, we will actually maintain the vertices that we visit on the same path by a stack. So a stack is the data structure which you add to the front and you also pop to from the front. Think about a stack of books. In order to get to the last book, you must actually remove all the previous ones. Now, the depth first search tree of a graph is the output of the vertices and the edges that were visited while running this depth first search. Typically, and we have seen the example in the previous lecture, the depth first tree typically gives very long branches. In extreme case, you could have one sequence. So the depth first search tree could give you a path which is of the length n minus 1, the number of edges in the tree. So the breadth first search tree is a lot better balanced. So there the number of layers is logarithmic, the 2 log of the number of nodes. Okay, here is the formulation. On input, we have a graph, 2 lists, the vertices and the edges. We compute all the vertices that can be reached from the root. So this gives you actually the search structure. So this is the algorithm where we keep track of the vertices that are visited. So we call it here explored. It's important to have an array because in the while loop, we must very quickly decide in constant time whether we have visited a vertex or not. So the popping from the stack. So if the stack is empty, then there are no more vertices to explore. So it's important here is also once a vertex is explored, we're not going to visit it again. So a vertex that has been explored is not going to be pushed again on the stack. So that is important. Also, the W's, so the set W's of all the vertices that can be reached from the given route, that only happens, so we only add to W those vertices that are not explored. The algorithm terminates because we are in this course only looking at finite graphs. We have a finite set of cardinality n, and therefore the algorithm, when we have explored all the vertices, then the algorithm terminates. So this is the iterative formulation of the algorithm with the stack. So whenever we do the pushing, we actually make a recursive function call. So at first, the vertex V is the root R, but it gets popped and then it becomes one of the W's. Okay, what we do need is an extra data structure. If we have hit a dead end, we must go to the parent of the vertex, which could be the root. And for that, we need another array that could be as long, that typically is as long as the total number set of vertices. So we have an edge VW. We must be able to go back to the W. So we will assign the parent. And then when we come back, we have to make sure that we can add the right edge to the depth first search tree. Okay, so let us now state the complete algorithm, complete with the data structures, also with the output of the depth first search tree. So T lists all the vertices and all the edges that can be reached from the root node. The initialization will initialize all the nodes to false, except of course the root. The root is actually will be explored. So that might still be an issue here on this slide. No, I'm sorry. So when we pop something from the stack, it should not be explored. So if we would have set the explored for the root equal true, then the algorithm would simply have stopped. Okay, we check whether we can reach, we actually check the edge set for the next vertex connected to the current vertex V, and we actually go to that node. So we actually are going to add the edge to this. So we are working with this parent So we can then, when we construct the edge sets of the tree, we know which path we followed. So we know which edge to add. Okay, here is the equivalent theorem to the breadth first search algorithm. So the algorithm is actually completely different from the breadth first search, but it runs in the worst case in a time that is bounded by the sum of the vertices and the edges. So the initialization is linear in the number of vertices, that will be okay. Manipulating that stack, pushing and popping, takes a constant time. One very natural data structure is a linked list. So you could say a stack is a list with very specific accessing protocols. You only insert to the front and you only delete from the front. And this runs in constant time. Again, one of the exercises that was assigned. Now comes the critical property, and here it is stated. So how many times do you need to add to the stack? Well, that is depending on how many neighbors you have. So we actually are going to explore the vertices based on the degree. So we have the property that the sum of the degree equals twice the number of edges. So twice the number of edges is still O of M. Then we have this parent data structure, which is just an array. Also, because it's an array, we can access it in constant time. O of n plus O of m is O of n plus m, and that proves the theorem. Okay, so that went rather quick. So let's go now for the remainder of the lecture. So I'm not yet halfway. On 1/3 of the lecture, we're going to consider two different types of applications of the graph traversals. The first application is that if we have a graph that is connected, then we are done. But we may have graphs that are not connected. In that sense, we may want to compute the number of connected components. In some sense, we will compute a forest, a collection of trees. So here is a natural algorithm, which I hinted at earlier at the very beginning, why we might want to be interested in these traversals. You compute the one of these search trees, doesn't really matter breadth first or depth first. If you have as many vertices in your tree as the value of n, the total number of vertices in the graph, then you're done. Otherwise, you may still have vertices left that were not visited. And therefore, you continue computing again a breadth first or a depth first. So this is a very straightforward algorithm. If you do it like this, then the obvious cost is n times n plus m. Now, of course, with a disconnected graph, you very unlikely have that m is of order of n, but it could still have that be that you have one very large connected component close to n square and then many isolated vertices. So it could be that you cut the graph in half, you have n over 2 vertices that are isolated and the rest is completely connected. So the n over 2 to the power 2 is still n squared. So you would still end up with an algorithm that is n times n squared. You would end up with a cubic cost, which is quite bad. Now the question therefore is, can we derive a sharper upper bound? So this is mainly an analysis question. So our algorithm will not start running faster once we derive another upper bound. So from a practical purpose, this algorithm that we have described here is perfectly fine. We will show that you can derive a much sharper upper bound. So we need a lemma for that. Um, so if we have two vertices, then either their connected components are actually either identical or there are disjoint. It looks like a basic lemma, but let's prove it anyway. Assume that for the two vertices there is a path between them. So that means that if we start searching breadth first or depth first, then the tree will actually contain W starting from V. So that means that the vertices breadth first, search depth first will actually be identical. So they will be in the same connected component. So that is what it means to be in the same connected component. Otherwise, the other case is that there is no path. Assume that we're going to prove this by contradiction. So assume that there is actually a path, and we will derive at the contradiction. So in that actually, if there is no path, then actually they are in the same connected component. So in this case here, we are in the second case. So you are, both vertices are in disjoint connected components if there is no path. So that states a property that we will need in the proof of the theorem. Okay, here it is. You see that actually computing the set of all connected components runs in the same time as the graph traversal. So in some sense, this is a surprising theorem. The worst case is of order n plus m. All right. I should have stated this. So the lemma seemed rather straightforward and kind of so what, but it actually means that the work that you spend depends on the size of the connected component. So we can say that we have k components in our graph, and the ith component can be computed by the cost n of I and m of I. So it's important to realize that we started with two variables, two parameters, the n vertices and the m edges, but now we will translate this into 2 times k parameters. So we have the total number of vertices partitioned, and that's actually also the point of the previous lemma. Every vertex belongs to exactly only one connected component. Now, if we run the algorithm, we can now express the constant. So we can use the same constants. So up to from a certain size on, the cost will be bounded by a constant c times ni plus mi. So it's important here also to realize that the k is a fixed constant. So k does not grow. So what is growing in this consideration here is the n and the m. If we would, on the other hand, have k equals to n, then we would be summing up constants. And again, as many constants as the total n and the total m. So that is important to consider here. K is a constant. Okay, so the step 2, where we had n times n plus m on the algorithm, is actually now running in linear time. And when we add this to the n plus m, we actually have what needs to be proven, the order of n plus m. Okay, so this is an important analysis that shows that the computing of the set of connected components, or computing the number of connected components, can be done in time linear in the number of edges plus the number of vertices. Okay, so the second part consists of um, figuring out whether a graph is bipartite or not. So in a bipartite graph, you can partition in two bi, and you can partition the vertex set in two, such that in one set there are no edges between the nodes, and also in the other set there are no edges between the nodes. So actually we start with a counter example. So what actually, in terms of coloring, it means that you can color a graph so that adjacent nodes have different colors. In a bipartite graph, you only need two colors. So here I'm using green and red for the complementary colors. And you see two examples. So the middle graph is a bipartite graph. So 1 and 3 are in the same vertex set, and 2 and 4 are in the same vertex set. So in some sense, there is a canonical way to displaying the bipartite graphs. So graphs in the middle, the graph in the middle and the graph at the right are actually the same graph. So what you do is, once you have colored the nodes so that two adjacent nodes have a different color, then you pick all the nodes of the same color, put them in the left vertex set, and all the other ones of the other color, put them in the right. The first graph with three nodes is actually a triangle, and there you need three different colors. So that is an example where the graph is not bipartite. It's actually the simplest example of a graph that is not bipartite. So as soon as you have a triangle in your graph like that, if that is a subgraph, you know that the graph is not bipartite. Okay, the definition states this formally. So we split the set V into sets U and W. And for all u's, little u's, all vertices in U, all vertices W in the big W, we have no edge. Okay, what now characterizes a graph that is bipartite? Well, actually, we can say it in the opposite way. We actually observe that if we have a triangle, then the graph cannot be bipartite. And a triangle is a very special case, the smallest case of what is an odd cycle. So all these graphs that you see here have cycles. So we have essentially a square at the middle. So we have, but the number of edges in that cycle is even. So obviously a bipartite graph has no odd cycles. So that's one direction in the theorem that follows directly. So we have a characterization of a bipartite graph. A bipartite graph doesn't have any odd cycles, and a graph with no odd cycles is bipartite. So this is a characterization of a bipartite graph. So the if and only if. All right. We are going to prove this theorem with an algorithm. So sometimes, like in the previous case, we have an algorithm and we do an analysis. Here we have an algorithm, and if it is correct, it will actually prove the theorem. Okay, um, we start off with a connected graph. We are going to initialize, so we grab our colors. So we have two colors, red and green. At the root, we start with red. At the neighbors, we color it green. The neighbors of the neighbors is again red. So you see that we are again doing the breadth first search algorithm, layering the um, vertices, and color them. Okay, so I should actually say that a tree is actually doesn't have any cycles, so a tree is by naturally it is bipartite. Okay, we started out with red as the color of the root, uh, one the color of green. So the index of the layer, if it is even, then it's all the vertices are red. If it is uh, odd, then all the vertices are green. And now actually comes the important phrase that I should have. So if we think about trees, we actually consider only one edge, but now actually we look at within one layer, and we can do is layer after layer. Uh, Within the layer, we check if there are any connections, because all the vertices in the same layer have the same color. Here, if there is um, no edge between, then actually as long as that happened, it is bipartite. So here you see the algorithm to actually running the breadth first search algorithm. We computed the shortest paths, but actually we also are going to decide whether the graph is actually bipartite or not. Okay, if the graph is not bipartite, then actually you can make a triangle. And actually you can make in general an odd cycle. So you have, you may have a triangle if U and V are directly connected to the to a node in the previous layer. So because they are in the kth layer, there is an edge from U and V to the previous layer. But it doesn't necessarily say that these two vertices are connected. Now there is a root in this tree, so we may have to go up k steps. So we will have an odd cycle. So we proved, or there was the proof by induction exercise of the previous lecture, where the nodes in the kth layer are at distance k from the root. So we may have a shorter odd cycle, but we will certainly have one odd cycle if we go all the way up to the root. So from U, there is a path of k edges to the root. From V, there is a path to the root with k edges. So, and U and V are connected, so we have an odd cycle. So you see that we have proven the theorem. So by, in a very constructive manner, we have, so the proof is constructive. There is no distinction between a proof and the algorithm. So this is also the design of an algorithm now. This part of the course, design and analysis of an algorithm by reasoning on a characterization of what is a bipartite graph, we can efficiently compute whether a graph is bipartite or not. And this runs in time n plus m. And that is actually what the final major result of this lecture said. We run the breadth first search algorithm, and we will have a test whether the graph is bipartite or not. Okay, we have to show this. So when we run the breadth first search, we compute the layers and we color the nodes in the even indexed layers red. The ones in the odd indexed layers are green. So it's just adding an extra attribute. So coloring red or green is just constant. So we add another label. Testing whether we have an edge for all the nodes in the same layer requires the traversal of the adjacency list. And how do we do this? Well, we have the adjacency lists that we have the property still, the sum of the degrees of the vertices equals 2m. So actually we have to go through this adjacency list m times. So there have a tight upper bound. Okay, so we have the extra instructions, the big data of m. The coloring is actually, if you like, big data of n as well. So, but adding to a big O a big data does not change anything. So it's just adding a constant in front of the m. And that gives the proof. So in the design of algorithms, and we will, at the end of the course, we get to NP completeness, is mainly a way that we can transform one problem into another problem with only polynomial time, preferably in the same dimensions, with some extra polynomial time operations. So the algorithm of graph traversal is equivalent to computing all connected components. It is equivalent to testing whether the graph is bipartite or not. They all have the same worst case upper running bound, n plus m. Okay, I said about equivalence. So how would you decide if there is an odd cycle in a graph? This is another theorem, which is essentially equivalent to the previous theorem, using the characterization of a bipartite graph. A graph is bipartite if and only if the graph doesn't contain any odd cycles. Now you have to write an algorithm that actually returns true or false given a graph with n vertices and m edges. And you can use the breadth first search algorithm and also doing the check. And the proof that the algorithm runs in time n plus m starts by stating the theorem. Stating the theorem that the algorithm to decide whether it's an odd cycle in a graph with n vertices and m vertices runs in time big O n plus m. And then you go over the same arguments that we had. So the algorithm, the exercises appear rather superfluous and rather pedantic, but what is very important here with these exercises is that you can formulate, you can talk about the subject in your own language. I'm trying to make the slides as self-contained as possible. Please also read the textbook. That is another language, another way of using words to talk about the same things. You should find your own way of talking about this. All right, we have a holiday in front of us, Wednesday, 19 June. You have this essentially more time than with the first homework collection. So here are the problems that will be collected at the end of the second week.